Greetings everyone. Our project is swarming Proxima Centauri. My name is Marshall Eubanks, I'm the PI. And I thought we'd start by showing you a movie. This movie is the fun part of the Proxima B mission. We're going at 20% of the speed of light and it's happening in real time, so things happen fast. So here's our Coracle probe. We have a lot of them, we're sending 1,000. We're going to pivot around and we're going to look at the star itself. There are actually 1,000 probes in this video. So here's the star Proxima Centauri. We're approaching it. We're approaching the planet Proxima B. We're going to do a close flyby of it. You can see Alpha Centauri AB off in the distance there to the right. And you can see there's, of course, a bunch of swarm members here. And again, Proxima B is supposed to be a rocky planet, is thought to be a rocky planet. It is a little bit more massive than the Earth, and we're going to fly by about right now. Again, this is real time. This is more or less what you would see, except for a redshift, a blue shift and then a redshift. And we had the artists do the planet as an eyeball planet where you have a central warm spot surrounded by a cold zone, because we think this planet's probably rotationally locked. So thank you. Let's go on. Good afternoon. Well, we've seen the video, and now we're going to go through and we'll show you what's behind the video. And there is a fairly large agenda here, but I think we can get to all of it. So let me start with some basics about where we're going in the mission. Where we're going is Proxima Centauri, the nearest star to the Sun, part of the Alpha Centauri system, and its planet Proxima B. Proxima B is a rocky planet, a little larger than the Earth. We know a little more massive than the Earth, presumably also a little larger. The radiuses here are all assumed based on models. That is the planet in the habitable zone of Proxima Centauri, and so that's our mission target. Where we'll look for the other planets, but that's the target we're going to focus on. And we're going to do this using laser sailing at point 2C, and we're going to do it with our Coracle probes. You saw the Coracle probes. Here they are again, with the labels. The things you might not have noticed is the side lasers, or the little red lasers. That's how we communicate from probe to probe over maybe a few thousand kilometers. That's essential for making the swarm coherent. And then the round things are annuluses. And the annuluses is how we both see, how we take images, and how we communicate back to Earth. So they're mission critical. And this is it in real life. This is with Robert Kennedy, who put one of these together. This particular unit was sent to the World Science Fiction Convention in Glasgow, Scotland. It was a fairly big hit, I understand. And we have one here in Pasadena. So the Coracle is 4 meters in diameter. It is only about 2 centimeters thick, and it will have an armored rim on one side. And most of the time we expect to fly rim on. And the reason for that is very simple. The interstellar medium, even though it's only about 0.1 particle per cubic centimeter, will be a bath of 10 MeV protons as we're zooming through it at point 2C, and that will cause erosion and damage to the structure. And so we want to have an armored rim so that as we go forward, that rim gets eroded, but not the rest of the spacecraft. And essential to this spacecraft will be the folded optics, which you see here in this image. That's how we will get resolution comparable to, say in this case, the LORRI camera on New Horizons, but with much less mass, because it'll be 25 centimeters aperture, but only about 8 millimeters thick. Making this mission work, operational coherence is essential to making this mission work. By operational coherence, we mean that the whole set of probes act as a unit. Now notice that doesn't mean phase coherence, photonic phase coherence. We won't be able to do that. But if we have good enough clocks and we have range measurement by lasers, we can determine where we are to a few centimeters. We can determine what the relative clocks are to the more or less the same level. And we can then act as one thing. And the crucial part of that, we can do that with a lot of things like taking pictures of the planet and so on. But the crucial part of that is what we call the wall of light. The wall of light is when all the probes send one coherent, but not phase coherent, just photonic coherent, set of photons back to Earth so that they can be received all together. We think with that we can get a 1 kilobit per second data rate back, and we can therefore send something like 4 gigabytes a year back to Earth, and that's enough to get good data and really understand the system. So here is a video image of the wall of light that Paul Blase prepared. The probes don't have to be in a line. They can be at different directions from different distances from Earth. They have to know that relative distance so they can send out the pulses time so that once they leave the swarm, they're all in one line going forward. At Earth, that would amount to a spot with the current model of about a meter thick spot of photons that is about 1 million kilometers across. That's pretty amazing. We think we can do it. We've identified various problems that will have to be solved to make this a successful mission. One of them is what we call image smearing. It's very easy to understand. We would like to get 60 meters resolution, which we think we could do with our cameras. The light at Proxima b is going to be comparable to the light at Jupiter in the solar system. We think we're going to be using something like 20 millisecond exposures. We travel 60 meters in 1 microsecond. So to do 20 milliseconds, we have to somehow, that would be a tremendous amount of a factor of 20,000 motion smearing. The way to do that is through time difference imaging, time delayed imaging, where we take the photons, the planets going this way, we take microsecond duration exposure, say, and we shift each exposure by the right amount so that the photons that fall all line up on the same pixel in the resulting image. That's actually being done right now in the Juno cam and orbiting Jupiter. It's been done before with various spacecraft. It's just we're talking about doing it with about 10 to the 4th more, a higher velocity. That's a technological advance, but we think we can do it. And by the way, that also means you're going to generate we would generate lots and lots of data, terabytes a second at full data rates. And there's also velocity shifting. A human would definitely know the redshift and blue shift, as we're seeing in this video that Adam Hibbert prepared. A green chlorophyll planet, for example, would go from blue on approach to orange on recession, going away when it's redshifted. That has to be accounted for too, or your colors will just be a mess. And so that will have to mean velocity shifting. You'll have to have narrow bands in your photography, and then you will have to shift the photons by the right amount so that all the photons of the same color line up together, and you have a nice clear picture in color as well as in black and white. I don't think anybody's ever done velocity shift integration before, because I don't think they've had to. We want to do transmission spectroscopy. Transmission spectroscopy means you need a bright source that you're setting, say, behind the planet. So it's going through the atmosphere. We have the brightest natural sources are Alpha Centauri A and B. They're about 13,000 AU away. It's a nice distance. They are very small from that distance. They're point-like, and they're brighter than Venus is on Earth. They'll make excellent targets for transmission spectroscopy. With that, we can get spectral lines in the atmosphere. We can look for layering in the atmosphere. And we can also use the drive laser as a monochromatic source. So we can't do spectroscopy, but we can do photometry, transmission photometry, and that would be really good for looking for rings around Proxima b, or maybe the other planets too. We think with this we have an excellent chance of detecting biosignatures in the atmosphere of Proxima b, and technosignatures if they're there. We can look for methane, we can look for oxygen, we can look for all kinds of gases, including things like chlorofluorocarbons. And we can do this both with photography and imagery, and also with transmission spectroscopy. And we also have the additional advantage that we can look for large objects, like either biological, like a forest or a coral reef or something, or a technological feature like an airport, port, something like that. We'll have to select the data to send it back properly. We will have a factor of 10 to the 4 maybe between the data we collect and the data we send back. And we think the best way to do that is with agents that are looking for different things. We're borrowing this from the LSST Roman telescope. The basic idea here is you have an agent, maybe an agent's looking for moons, suppose it's looking for circular objects against a black sky. Maybe another agent is looking for a glint from the ocean or something like that, or is looking for the presence of an ocean. So it's looking for different features in its own way. Some may be simple, some may be complicated. And then you rank all the data that way and you say, here's the next best picture to send back. And we have this OESF flood, as I call it, where we observe, evaluate, select the data, and then flood that to all the probes, because they all have to have the next data object, picture or whatever, to send back. Because if they don't have that, then, I mean, they have to have that to do the wall of light. They all have to send together. And by the way, we've also noticed that the Proxima ephemeris errors and the Proxima b ephemeris errors are too large for this mission to be successful right now. We need better parallax, better proper motions, and a much better orbit for Proxima b. So in conclusion, we feel like this is very, very exciting. We feel that these techniques can be used all over the solar system, and we feel like we can get really good science that you can't do from Earth at Proxima b. And we welcome further questions later. Thank you.